Okay, a very good morning to our distinguished presenters, guests, ladies and gentlemen. Welcome to the parallel session of ICPM 2020. Excited to welcome all of you. I am Dr. Chiu Tiam Leng from Department of Chemical Engineering. So I will be the chairperson for this session. Okay, so without further delay, let's welcome the welcoming our department chair, Associate Professor IR, Dr. Abdul Halim.
Good afternoon, ladies and gentlemen. On behalf of the organizing committee, I wish to extend a warm welcome to you for attending the International Conference on Process Engineering and Advanced Materials 2020, which is well known as Icpeam 2020. This is the sixth conference in a series that began in 2010 under the World Engineering Science and Technology Congress umbrella. Icpeam 2020 is a chemical engineering-based conference with the theme Sustainable Future, the Inevitable Change. Our goal is to spark a broader discussion on the opportunities and challenges of the current technological innovation, including the Industrial Revolution 4.0, in achieving a sustainable future. I believe that Icpeam 2020 is the ideal platform for scientists, engineers, industrial experts, academicians, and scholars to disseminate the most recent findings in their respective field. The conference also provides excellent opportunities for the participants to exchange new ideas and experience, as well as to establish research and business relationships with global partners in preparation for future research collaboration. This year's conference has attracted over 100 participants. Our technical program features 5 tracks, which include green and advanced material engineering, sustainable process development, process system engineering and optimization, advanced kinetics and thermodynamics engineering, as well as in industrial tracks. Furthermore, the organizing committee has invited 3 distinguished plenary speakers to share their experience and knowledge. I would like to extend a warm welcome to our plenary speakers, Datuk Muhammad Arif Mahmud, Professor Junji Inukai, and Professor Chris Aldrich, who represent leading experts from the industrial and academia. I sincerely believe that this conference exchange of ideas will help to establish new connection, create collaboration, and cultivate friendship between academia and industry. Last but not least, I would like to express my gratitude to our co-organizers, participants, reviewers, sponsors, and organizing committee for their significant contribution to the conference success. I wish you a successful and a rewarding experience at Icpeam 2020. Thank you.
Okay, thank you very much. The welcoming remark from our department chair, Associate Professor IR Dr. Abdul Halim Shah. Okay, so welcome to this technical session. This is technical session 1 for the track Advanced Kinetics and Thermodynamic Engineering, as well as Green and Advanced Materials Engineering. So before we proceed to the presentation by each of the presenter, just a kind reminder to all our audience, if you have any inquiries related to the topic being presented, you may type your question in the live Q&A or discussion forum. Just click whether one of the icons at the bottom of your screen and type the question in the chat box appeared. Okay, the presenter will answer your question after he or she completed the presentation. Okay, without further delay, let us welcome the video presentation from the first presenter. So now we have the first presenter, Ms. Siti Muhira Muhammad Yusuf from University Technology Petronas. So she will be presented a paper entitled effect of monoethanoamine concentration on CO2 removal using continuous high-frequency ultrasonic reactor. So let's welcome the first video presentation.
Assalamualaikum and hello everyone. My name is Siti Munira binti Muhammad Yusof. I'm from University Technology Petronas Malaysia. For today I will present my study entitled Effect of Monoethanoamine Concentration on CO2 Removal using Continuous High Frequency Ultrasonic Reactor. So this is the outline of the presentation. First, we will go through the introduction, which include the previous statement on also objective of the study, and then we'll proceed on the literature review. In the literature review, we'll look at the theory, critical analysis, and also research gap, and then we'll proceed to the methodology to look at the experimental procedure, and then we'll proceed to the result and discussion, and finally conclusion. So there are a lot of technology has been used to remove CO2 from natural gas, such as adsorption, membrane, and also cryogenic. So among all those technology, adsorption is the most matured and well-established method. So for adsorption process, liquid is used to diffuse the CO2 gas from the gas stream. So the benefit of using the adsorption technology is that we will recover high purity of CO2. So for adsorption process, the most common contactor that has been used in the industry is the packback column. So using the packback column, it has a high mass transfer efficiency with low pressure drop. However, as we can see in the picture, the size of the column is very big. It is to increase the gas liquid contact time, and also inside the pack column there is a packing. So the packing will cause operational issues such as liquid channeling, flooding, and also foaming. So since there is a packing inside, it is less feasible to use a high viscosity solvent due to low solvent ability to spray on the packing, and also will cause the operational issues. The operational issues referring to the liquid channeling, flooding, and also the foaming. So recently there is a new technology has been invented for the adsorption process, which is the high frequency ultrasonic reactor. So from literature's issues that the high frequency ultrasonic reactor has high adsorption enhancement of up to 80-fold for batch system, and using a continuous system, it shows that the high frequency ultrasonic reactor has higher mass transfer coefficient as compared to the pack column. So since it has a high mass transfer coefficient, so this technology has a compact footprint. So as you can see in the picture, there is nothing inside the reactor, so it has no packing. So since it has no packing, it will reduce operational issues such as liquid channeling, flooding, and also foaming. And also, since it has no packing, so there is possibility to use high viscosity solvent. So however, since this is a new technology, so this technology is still in the research development stage. So next we'll proceed to the problem statement of this study. So higher MEA concentration provide higher amount of active MEA in a bulk solvent to capture the CO2 gas. Due to the absence of packing inside the ultrasonic reactor, it is possible to use high viscosity solvent to remove the CO2 from the gas stream. However, there is no experimental work has been conducted to investigate the effect of MEA concentration on CO2 adsorption in continuous high frequency ultrasonic reactor has been reported. So now we'll proceed to the objective of the study. It is to investigate the effect of MEA concentration on the CO2 removal using high frequency ultrasonic reactor in continuous system. So next we'll proceed to literature review. So what is ultrasound? Ultrasound is a form of energy that used to amplify the energy supply through wave propagation at frequency in the range of 20 kHz to 500 MHz. So ultrasonic radiation has two effects, physical effects and chemical effect. So physical effect can be divided into acoustic streaming, fountain formation, and also atomization. So for the chemical effects, it refers to the acoustic cavitation. So in the acoustic cavitation, there is a implosive collapse of bubble in the liquid. So the collapse of bubble is in high temperature and pressure. So it will release free radicals that enhance the chemical activity in the solution. So next, so for the physical effects, as you can see here, first it has a fountain formation. So the fountain will increase the total surface area of the liquid. And also there is atomization. Atomization refer to the formation of micro droplets. So these droplets will increase the gas liquid interface area. And also inside the solvent there is acoustic streaming. So the acoustic streaming will provide good gas liquid mixing and also will reduce the liquid film resistance. So these physical effects will enhance the mass transfer process. So next we'll proceed to the literature review. So this since high frequency ultrasound is a new invention for absorption process, so there is a limited study has been conducted. First, for batch system. So as you can see here, for batch system, there is one study that studied the effect of MEA concentration on the removal of CO2 gas. So from the study, it shows that higher MEA concentration resulted to higher mass transfer coefficient. However, since this is batch system, it doesn't involve the movement of liquid in and out of the reactor. So we cannot compare the performance to the packed column. So for continuous system, there is two study has been conducted. However, there is no both study shows that higher mass transfer coefficient is reported as compared to other contactors such as packed column. However, today there is no work has been reported on the effect of solvent concentration on CO2 removal using high frequency ultrasonic reactor in continuous system. So next we'll proceed to the methodology. So this is the high frequency ultrasonic system that used for this study. So the temperature of the reactor is maintained at 30 degrees C using a water bath, and then mixture of gas, which is methane and CO2, is fed into the reactor, and then the pressure of the reactor is maintained using the bed pressure regulator. And after we feed in the gas, we feed in the liquid, and then we'll turn on the power supply for the ultrasonic. And after that, the inlet and outlet gas sample is analyzed using the IR analyzer to show to look at the composition, the CO2 composition in and out of the system. So this is the operating parameter that has been used for this study. So we use a fixed CO2 concentration, which is 20%, 50 bar, pressure of 50 bar, temperature 30 degrees C, ultrasonic frequency of 1.7 megahertz, ultrasonic power of 33 watts, and also for MEA concentration, we varied the concentration, which is 30 weight% and 70 weight%. So this is the result of the study. As shown in the graph, it shows that higher concentration resulted in high mass transfer coefficient. It is due to high capacity of active MEA in a solution to remove CO2 from the gas stream. So however, in a study done by Sitamiku et al. 2008, it shows that the increase in MEA concentration resulted in low increment of mass transfer coefficient. It is due to the low spreading ability on the packing surface. So, however, from this work, it shows that high viscosity does not affect the performance under the ultrasonic irradiation. It is because even though at high concentration, the viscosity of solvent is higher. However, since we have the ultrasonic irradiation, we have we create the formation of fountain, atomization, so that will increase the gas liquid interface area. So, and then we also have the acoustic streaming. The acoustic streaming will have a mixing effect, so it will increase the diffusivity. Since we increase the diffusivity, so it will result in a higher mass transfer performance. So next is the conclusion of the study. So this work has shown that the increase in solvent viscosity does not affect the mass transfer performance of the adsorption process using ultrasonic irradiation system. It is due to the physical effect of ultrasound that increase the gas liquid interface area and also reduce the liquid film resistance. So this technology shows that it has great potential for the enhancement of adsorption technology since it can provide higher mass transfer performance as well as higher flexibility of solvent selection as compared to conventional packed column. So that's all for my presentation. Thank you for watching.
Okay, thank you very much for the video presentation from Munira. So now let us open to the floor for the questions. So a reminder to all, if you have any question to the presenter, you can just click the icon live Q&A discussion forum to drop your question over there, and the presenter will answer your question accordingly. Okay. Okay, since there is no question yet from the floor, maybe I can ask Miss Siti Munira a question. Okay, Miss Siti Munira. So I just wish if you can share when you investigated by using the high frequency ultrasound, what would
Hello?
hello?
Hello, sorry, I didn't hear your question just now.
I repeat the question again. Okay, when you perform investigation using the ultrasonic reactor, what was the challenge you faced?
The
Can you
challenge.
share yes, yes.
Because this is a new technology, so I need to know more about. I didn't know what the problem might be. So for my from my experience, the challenge is more on how to optimize the process, like the the design of the reactor, something like that. So they actually when we want to increase the interfacial area, right? So how to get the fountain a little bit higher, it has something related to the solvent, the height of solvent inside the reactor. So before I do the actual experiment, I need to tune first which height that I should maintain, so that I can get the optimized fountain height for my project. So for this project, it has before I can get the real result, I need to do a lot of try and error first to get what is the most good result for that project.
Okay, thank you so much for your sharing. I can see actually it is very challenging for you even to make sure all your reactor are in right place before you can run the experiment. Okay, so I can see actually there is no questions from the floor. So thanks again, Miss Siti Munira, for your sharing.
Okay, thank you,
So
Dr.
okay, with this, let us proceed to the second presentation. So we have the second presenter, Miss Fateh from University Technology Petronas as well. Okay, her video presentation will be presenting a project entitled The Influence of Acoustic Power on Chemical Absorption of CO2 Using Low Kinetic Solvent. So without any further delay, let's video presentation.
Hello, my name is Fateme Shokrallahi, and I'm going to present the influence of ultrasonic power on chemical absorption of bulk CO2 using a slow kinetic solvent. Regarding the introduction, natural gas has less environmental issues compared to other types of fuels. Therefore, the demand for it is expected to increase by more than 60% till 2040. It depends on reservoirs condition. Natural gas has significant amount of impurities such as CO2, H2S, or even CO. To increase the heating value of the gas, to minimize operating and maintenance issues, maintenance costs, to maintain the environmental issues, or even to increase the selling price of the gas, such impurities must be separated from the gas. Absorption, adsorption, cryogenic, and membrane technologies are widely used processes to purify natural gas. Between them, absorption, and especially chemical absorption, is the most widely used separation process. But despite all recent developments for this process, some problems such as large column size or maintenance and operating issues still exist. Therefore, to assist the absorption process, new alternative technology, potential technology, or alternative technology is essential to be developed. The use of ultrasonic radiation, and especially high-frequency ultrasonic radiation, as one of the intensifying technologies, has several applications in different research areas, such as food industry, medical treatments, or even enhancement of multi-phase reactions. However, with such applications, the use of ultrasound in gas separation processes, in particular the CO2 absorption process, is limited. Generally, during the CO2 absorption process, there are three main steps, including vapor liquid mass transfer, liquid mass transfer, and liquid chemical reaction. Due to the presence of chemical and physical effects of the ultrasonic radiation, all these steps can be affected. Streaming, atomization, and fountain formation are the main physical effects of the ultrasonic radiation. They can provide good mixing and enlarge the surface area between the gas phase and the liquid phase, and therefore affect the mass transfer process. On the other side, the presence of ultrasonic chemical effect might also enhance the chemical reaction happening during the CO2 absorption process. Influence of several parameters can be investigated, such as frequency, power of the applied sound, temperature, pressure, solvent properties, or even sonication time. The scope of current work is studying the effect of ultrasonic power as a critical parameter on CO2 absorption using a slow kinetic solvent. Methyl diethanol amine, which is known as MDA, is one of the chemical absorbents for the purpose of natural gas purification. It has several advantages over the widely used MEA, such as high CO2 absorption capacity or less regeneration heat demand, but the main disadvantages which makes it less practical is its low chemical reactivity with CO2 and therefore low absorption rate. It is guessed that the high frequency ultrasonic radiation has this potential to enhance the absorption rate of such slow kinetic solvents and make them more practical. The experimental setup is shown here. The batch reactor has two main parts, including top cover and body. Top cover has 5 different ports, including the temperature and pressure sensors, the gas inlet and gas outlet, and conductivity probe. A 1.7 megahertz transducer is placed at the bottom of the reactor for direct contact with the solution. It is worth noting that the transducer converts the electrical power into the ultrasonic radiation. The reactor is then filled with 100 ml of MDA aqueous solution. The solvent's temperature could increase slightly. Therefore, to maintain the solvent's temperature, we put the reactor, the ultrasonic reactor, in a water bath system. Then the pure CO2 gas is compressed into the gas storage vessel. After that, adjusting valve number 1 and valve number 2 with a back pressure regulator enables us to pressurize and control the pressure of the reactor. It should be noted that during this work, the absorption rate was measured and calculated using the CO2 pressure drop profile. Regarding the result, as I mentioned earlier, ultrasonic power is the output of the ultrasonic system, while the total power is the input of the electrical power system. The effect of ultrasonic power on CO2 pressure drop profiles are shown here in these two figures. This figure actually shows the full-time scale, while this one shows a small scale for a clearer view. The initial pressure, the initial CO2 pressure was 11 bar, the MDA concentration was 58%, and the temperature was 70 degrees C. The ultrasonic power varied from 0 up to 15.3 watts. I have to mention that the range of operating parameters was selected based on the limitation of power supply, ultrasonic system, and also solvents specification. As can be seen in these two figures, in these two graphs, the results indicate that by applying higher ultrasonic power, the pressure drop is significantly faster. The faster pressure drop means that higher ultrasonic power can enhance the CO2 absorption rate, as shown here in this feed. This enhancement can be due to the fountain formation on one side and also free radical generation on the other side. Actually, the streaming force at lower power is not enough to overcome the liquid layer surface tension and to form the fountain. The absence of the fountain actually induces a minor changes in the CO2 absorption rate. While by applying sufficient ultrasonic power, the ultrasonic fountain can be created. A specific amount of the liquid inside the fountain can be atomized, and due to the atomization, a specific number of liquid droplets cover the gas phase. Therefore, sufficient interfacial area between gas and liquid phase is provided, which improves mass transfer. On the other side, ultrasound actually can trigger sonochemical active bubbles and facilitate chemical bond breaking. In other words, increasing ultrasonic power disrupt bubble dynamic as it helps bubble grow unusually. The implosion of these bubbles provide a unique environment for chemical reactions as highly reactive free radicals are formed. The generated free radicals can react quickly, react with other species inside the liquid, diffuse into the liquid bulk. Therefore, they can initiate, promote, or alter several reactions happening during the CO2 absorption process. As a conclusion, I can say that high-frequency ultrasonic radiation is a new potential technique to assist the absorption process of CO2. In particular, it has the high potential to improve the absorption rate of the slow kinetic solvents without adding any rate promoters. Moreover, the efficiency of the ultrasonic assisted system significantly depends on power and also frequency. The influence of ultrasonic power on the CO2 absorption rate by using MDA was discussed in this presentation. The batch experiments results indicate that high-frequency ultrasonic radiation with the frequency of 1.7 megahertz can significantly boost the CO2 absorption process, CO2 absorption rate, in fact, in unpromoted MDA solution. Based on findings, the high-power ultrasonic assisted absorption system using 58% unpromoted MDA can provide up to 25-fold times higher absorption rate than the case without ultrasonic radiation. This improvement is due to both the physical and chemical effects of the ultrasonic radiation. The physical effect, as I mentioned, improves the absorption through the fountain formation and atomization, while because of the formation of highly reactive radicals, the sonochemical effect improves the absorption mechanism and also reaction pathway. These are the references that I used in this presentation. Thank you so much for your attention. I also want to thank UTP for organizing this conference.
Okay, thank you very much for the nice presentation from Ms. Fatima. So now let's see if there are any questions. Okay, I think in the live Q&A, there are 3 questions from Ms. Fatima. We will see the time limit. Okay, the first question actually from Dr. Lamanki. Okay, do you have the correlation between ultrasonic power with respect to ultrasonic frequency?
With respect to the frequency, no, I don't have such correlation between them, because in our case the frequency is somehow fixed because we wanted to see the influence of the high frequency. So we set the frequency up to 1.7 megahertz fixed, and then we just check the influence of the ultrasonic power.
Okay. Okay. We have second questions, I think from, okay, Ms. Shafika Saleh. Okay, what is rich and mean loading, if you can share?
The amine loading is because MDA is a slow kinetic solvent, it can absorb one mole of MDA can absorb just 1 mole of CO2, and the capacity remains same for this experiment. So it's 1 mole.
Okay, thank you for your sharing. Another question from Ms. Noor Karuniza Talib. Is there any issue with foaming formation when you apply this ultrasonic technology?
During the experiments and based off my experience, there was no foaming because of the nature of the MDA. That's why I choose the MDA. MDA is a slow kinetic solvent which has lots of advantages over the other chemical solvents used for the CO2 absorption process. One of the main advantages is less foaming tendency during the absorption process. So there was no foaming during the process.
Okay, thank you for your sharing again. I hope your answer it do address the concern or question from the audience. So audience question, maybe you can still drop your question into the live discussion forum, because so far we still have about 2 minutes time for the Q&A session. Okay, I can see actually there are no more questions from Ms. Fatima. So Ms. Fatima, thank you so much again for your sharing. Okay,
Thank you.
good day to you.
You too.
Okay, now let us proceed to the third video presentation. We have the third presenter, Mr. Ahmad Zaki Abbas from Petronas Research Malaysia. Okay, his project entitled HIC and SSC of carbon steel in high partial pressure CO2 environments with elevated H2S. So without any further delay, let's welcome the video presentation for Mr. Ahmad Zaki Abbas.
Assalamualaikum and hello everybody. Welcome to International Conference on Process Engineering and Advanced Material. I'm Ahmad Zaki bin Abbas from Group Research and Technology Petronas Malaysia. Will present to you project titled HIC and SSC of carbon steel in high partial pressure CO2 environment with elevated H2S. This is my presentation outline. Start with introduction, methodology, result and discussion, and lastly conclusion. Pipeline made from carbon steel are susceptible to hydrogen-induced cracking and sulfate stress cracking. In wet hydrogen sulfide environment, in transporting large amount of hydrocarbon gas with CO2. Wet hydrogen sulfide cracking is commonly classified into 3 categories, which is hydrogen-induced cracking, sulfide stress cracking, and stress-oriented hydrogen-induced cracking. Hydrogen-induced cracking, HIC, is type of sour corrosion that occur especially in carbon and low alloy steel when atomic hydrogen diffuse into the inclusion and combine to form molecule hydrogen at inclusion. Meanwhile, sulfide stress cracking, SSC, is a form of hydrogen embrittlement which occur at location where atomic hydrogen can diffuse at site of high internal stress, such as at gate boundaries, inclusion, and region of triaxial stress and notch. This study investigate the hydrogen-induced cracking and sulfide stress cracking behavior of sour service and non-sour service carbon steel, which is API 5LXCC5, under high pressure CO2 environment that containing 2000 ppm H2S to simulate the condition of high CO2 containing natural gas offshore pipeline. Material selection is based on the environment condition and must be carried out according to the guideline given in the NES MR0175 or ISO 15156. Petroleum and natural gas industry, material for use in HUS containing environment in oil and gas production. Many researchers have reported on corrosion behavior of carbon steel in high partial pressure CO2 environment, either in sweet or sour. But none has reported on HIC and SSC in the environment containing both high CO2 and elevated HUS. For the service to be considered as a sour service, the partial pressure of CO2 should reach above the 0.05 psi. Methodology. The material used in this work was API 5L65, carbon steel, sour service, and non-sour service. So it should be noted that sour service part has high purity of steel to avoid inclusion. The steel guarantee low sulfur, phosphorus, and other impurities. For the HIC test, the sample size about 10 centimeter, length 2 centimeter, width and height about 3 cm. For the for the searing sulfate test caking, the sample look like this. The searing sulfate test caking test specimen was stressed by tightening the bolt fixtures to the calculated deflection as measured by vernier caliper. 4 searing sample prepared with 2 stress level, namely 80 year strength and also 90 year strength. This is the equipment to conduct the HIC test. So the test based on NES standard TM0284. So the solution consists of sodium chloride and also acetic acid. The gas is for the next test 100% HUS, temperature 25 degrees C. For the field condition environment, the solution is 1% sodium chloride and 2000 ppm HUS, pressure 120 bar, temperature 25 and also 80 degrees C to simulate inlet and outlet of the pipeline condition. For the SSC test, the NES standard based on the TM0177, method C, standard searing test. The solution A based on the 5% sodium chloride and also 0.5% acetic acid. So the test is 100% HUS, 1 bar partial pressure, temperature 25 degrees C, duration 30 days. And for the field test, the solution is 1% sodium chloride with 2000 ppm HUS, pressure 120 bar CO2, temperature 80 degrees C. So the result from the HIC test, for the next condition, they are cracked on the non-sour service pipeline, and for the field condition, there's no crack. So we can see the crack at 2 locations. even though the field condition more than 0.05 psi, but there is no crack happen. But for the next condition, there's crack. Further investigation conducted on the crack area for the non-service part line, non-sour service part line. And we can see the crack happen. And for the sulfide test cracking, for the nails and the field condition, there are no crack for all sample. Conclusion, for the above result suggest that multi-crack happen on the non-sour service carbon steel for the HIC test following the NEST standard, and no crack were found for the sour service material for the HIC field test condition. And for the SSC ring test, there is no crack for both sour service and non-sour service part line for both NEST standard and also field condition. I would like to acknowledge my team member, Dr. Azmi and Dr. Muhammad Fidaus Suhul from Fatana Research, Cik Ahmad Mustaza from Good Technical Solution, and Dr. Mokhtar Ismail from UC Technology Petronas. Thank you.
Okay, thank you very much for the presentation from Mr. Ahmad. So now let's just open to the floor for the questions. If you have any question, please drop your question in the icon called live Q&A or discussion forum. Okay, while waiting for the question from the audience, maybe I could ask the first to Mr. Zaki. Okay.
Yes.
Mr. Zaki, I can see your work is very interesting because it is something new, but yet it is very, very challenging because it involves high pressure as well as with the presence of H2S. Okay, as I know, especially when we need to handle H2S very carefully. So could you share with us what would be the special care that happens when we handle H2S?
Okay, thank you for the question, Mr.
Yes.
Chairman. Basically, for the HUS, we have a dedicated or special room, special lab that have detector, HUS detector, and also for ourselves, we during the testing we are using breathing air system and also personal detector. So to protect ourselves first during the experiment, because HUS is very toxic gas, and we know the HUS is very heavier than air. So the room has special ducting system that will suck all the release gas to the scrubber system at the back of the lab. So in the scrubber system, they will dilute or absorb any HUS gas and release the clean air to the environment. So we protect ourselves and also we protect the environment.
All right.
Right, thank you.
This is very essential because I can see in your work, if I heard correctly, you are dealing with about 2,000 ppm H2S.
Yes, correct.
Wow, that is very high, I can say.
Yeah,
Okay.
that's why we wearing the breathing air system during the experiment.
Yes. Okay. So let us see if there is any question from the audience. Audience, if you have any question, please be reminded, click the icon of Q&A or discussion forum. Drop your question over there. So the presenter will share with you the answers accordingly. So maybe let us wait for about 10 seconds if there is any question from the audience for Mr. Zaki. For your information, Mr. Zaki is from PISP Malaysia. Okay, I can see actually there is no for Mr. Zaki. So Mr. Zaki, thanks again for your sharing. Thanks to you.
Thank you.
Bye.
Bye.
Okay, now let us move to the fourth video presentation. Okay, we have the fourth presenter, Mr. Ki Chong Hui from University Technology Petronas. So his project is dealing with effects and carboxyl functionalization on the photoluminescence size for property derived carbon quantum dot. So without any further delay, let's welcome the video presentation for Mr. Ki Chong Hui.
Good day to all of you. My name is Hui Ki Chong, a master's student from University Technology Petronas, Malaysia. The title of my paper is about the effect of amino and carboxyl functionalization on the photoluminescence property of rice-derived carbon quantum dot, RHCQDs. This will be the outline of my presentation. I will start with introduction, materials and methods, result and discussion, and finally conclusion. Introduction. So what are carbon quantum dots? Carbon quantum dots are small carbon nanoparticles that exist in quasi-spherical form with a size smaller than 10 nanometer. It is a new class of carbonaceous nanomaterials that have received much interest among researchers ever since its first discovery by Shi 2004 from the purification of carbon nanotubes. It has advantages like outstanding fluorescence properties, fair-cell synthesis, low cost, chemical inertness, low toxicity, good solubility, and good photochemical stability. So why rice husk in this experiment? Recently, natural precursors are preferable among researchers in synthesizing CQD due to their low cost and high abundance advantages. In Malaysia, rice production is around 1.7 million metric tons in just the year 2018. The large-scale production of rice can give rise to a huge amount of agro waste, in which rice husk is one of them. Therefore, in this project, rice husks are selected as the precursor to synthesize CQD due to its abundancy in the environment, low cost, fair-cell preparation method when compared to other bio-waste precursors. So, surface functionalization of carbon quantum dots. Carbon quantum dots with tunable photoluminescence are desired due to their demand in sensing, imaging, and photocatalysis application. Surface functionalization is a method whereby functional groups are introduced onto the surface of CQD. It is an excellent method to tune the photoluminescence and the band gap of CQD, and it actually helps in the enlargement of band gap of excitation, because it will actually shift the fluorescence from blue to red emission. However, there are limited research in the comparative study on the effect of acid functionalization agent and basic functionalization agent on the properties of CQD. Therefore, in this study, we will be using EDA as the amino functionalization agent and ascorbic acid as the carboxyl functionalization agent, and we will compare the properties of CQDs between two of them. Moving on to the materials and method. So these are the materials and instruments that will be used in this experiment. Rice husk will be used for the precursor of CQD. Hydrochloric acid will be used for the washing and pre-treatment of rice husk. EDA will be used as the amino functionalization agent. Ascorbic acid will be used as the carboxyl functionalization agent. Their water will be used throughout the experiment for washing, dilution, and solution preparation. So regarding the instrument, 100 ml Teflon 9 stainless steel autoclave will be used for the hydrothermal synthesis of CQD. Dialysis bag will be used for the purification of CQD. Vacuum filtration setup will be used to remove the excess solid from CQD sample. Moving on to the synthesis process. So the synthesis process, we will start with the pre-treatment of rice husk using HCl, followed by hydrothermal synthesis, then vacuum filtration, and finally dialysis in order to purify the CQD. So the functionalization will be vary at XML, in which EDA source, which is the amino functionalization agent, will be vary from 0.2 to 0.6 ml. The carboxyl functionalization agent, which is ascorbic acid, will be vary at 2.5 to 10 ml. So the characterizations involved in this experiment will be HRTEM, FTIR spectrophotometer, UV vis spectrophotometer, and finally PL spectrophotometer. So quantum U will be the main response in this experiment, in which quantum actually represents how much light is actually being absorbed by the particular CQD sample. So it actually indicates the performance of the CQD sample. It's calculated using the formula as below, whereby R is the reference fluorophore, in which in this case is quinine sulfate, in which QR normally is actually at 0.54. I is the integral fluorescence peak area. A is the corresponding absorbance of UVB spectra of respective CQD sample. N is the refractive index, whereby the ratio of N over NR normally kept to be 1. Moving on to the results and discussion. So morphology of carbon quantum dot are tested using HRTEM. So this actually indicates the successful formation of carbon quantum dot, in which carbon quantum dot actually exhibit spherical morphology. It actually exists in amorphous state. So in the case of nitrogen NiCQD, it actually exists in cluster form. This is actually due to the agglomeration caused by high surface energy in the CQD. Functional groups of carbon quantum dot are tested using FTIR. So strong absorption at 3,331 to 3,340 is actually due to OI stretching. CO bonding is found at 1,636 to 1,638. This actually indicates the successful formation of carbon quantum dot. So in the case of amino CQD, amino group are not being detected due to the little amount being used. For carboxyl CQD, CO bonding shows a high, slightly broader peak. This actually indicates the successful formation, functionalization of carboxyl group onto the surface of CQD. Moving on to the UV-vis analysis. So in the case of rice-husk carbon quantum dot only, main absorption peak are found at 212 and 281 with respect to N pi star and pi pi star of CO bonding. So for the functionalized CQD, main absorption peak are found at 220 nanometer and 400 nanometer, which actually due to pi pi star and N pi star transition of CO bonding. The addition of functionalization agent, as we can see from the figure, it actually show a red spectral shape to a more visible light region, which is around 600 to 800. The further addition of functionalization agent, from the graph we can see that N 0.6 and C 10 ml actually show a blue shift toward the left side. So for the photoluminescence property of carbon quantum dot, the addition of EDA actually show almost similar value of PL intensity. However, NCQD 0.6 show a slightly higher value of quantum U. So this actually due to basic reagent actually acts as a surface precipitating agent, which actually help to protect the surface functional group of CQD, which actually lead to a higher PL intensity. On the other hand, the addition of ascorbic acid actually lead to a drop in PL intensity. So CrCQD 2.5 ml is selected as the best sample. Acidic reagent actually lead to the protonation in the CQD, in which it actually lead to a very high electrostatic force that disrupt the carbon stacking in CQD. That actually lead to the drop in CQD and also the drop in the quantum U. In conclusion, additional functionalization agent actually shift the emission wavelength from blue to green region, which actually from 400 plus to 600 plus nanometer. Quenching of fluorescence is observed when we add the functionalization into the CQD. Photoluminescence of CQD is tunable under different amount of functionalization agent. From the characterization itself, NCQD 0.6 ml and carboxyl CQD 2.5 ml give the best result. So it can be concluded that fluorescence behavior of CQD favors a more basic and less acidic condition. So these are the references that are used for the presentation. So that's all for my presentation. Thank you very much.
Thank you very much for the Mr. Ki Hui. Okay, now let us open to the floor for the question. Audience, if you have any question, please drop your question in the icon for live Q&A or discussion forum. Okay, while waiting for the question from the okay, we have one question from the audience. It is from Dr. Opei Chen. Okay, could you share with us, will agglomeration affect the application of carbon quantum dot? If yes, how can we solve this issue?
Actually, I believe the aggregation will affect a bit on the application, but it doesn't really give a very much significant effect on that. But to overcome this, probably we can actually adjust the functionalization agent, make some adjustment onto the functionalization agent added, like maybe not this particular amount. Actually, this is just an experimental study. So yeah, to further improve this study, probably we can actually lower down the amount of the EDA.
Okay, thank you so much. I hope it answered the question by Dr. Oh. Okay, we still have another 2 more minutes for the questions. Is there any questions? Is there any more questions? Okay, while waiting for it, maybe I could ask a question to you. Okay, so I can see your project is very good because it used right husk as one of the raw material for your quantum dot. The right husk is very cheap. It is available abundantly. But I'm just curious, what would be the main ingredients or main composition in the right husk that make it to be potentially to be developed into quantum dot?
Actually, the amount of carbon that exists in rice husk is about 30 to 50% based on literature. So the carbon content is kind of high as compared to other precursors. So this is why, because I want to extract the carbon from the rice husk and actually functionalize them into rice husk. So that's the reason I choose rice husk as the precursor when compared to other carbon containing compound.
Okay. The reason I ask this because we might try to seek for other type of possible raw material as well with high carbon content. Can I say so?
Yeah, actually, in my study, I do compare a few different biomass also, but just that I find that rice husk is more easy to prepare. It's actually kind of small actually, as compared to other, like I do have some study about sugarcane baggers also, but they are very hard to pre-treat actually. Like when we receive that, actually, it's actually in a very sugary form. Actually, yeah, it's kind of
I
hard to.
see.
Yeah, the preparation method is kind of complicated as compared to rice husk.
Okay, okay. Thank you so much for your answer. Okay, I can see there is no more question from Mr. Ki Jong Hui. Okay, so thank you so much for your. I wish good day to you. Bye bye.
Thank you. Bye.
Okay, now let us move to our fifth video presentation. Okay, we have our fifth presenter, Mr. Mohidin from University Technology Petronas. Okay, his project is about screening of metal chloride anion based ionic direct conversion of hydrogen sulfide by Cosmo RS. Without any further delay, let's welcome the video presentation for Mr. Muhammad Shahir Aminuddin.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shahir Aminuddin from University of Technology Petronas, Malaysia. The title for my research is the screening of metal chloride anion based on liquids for direct conversion of hydrogen sulfide by Cosmo RS. Basically, this is the background for my research. As we all know, the H2S is a colorless, very toxic and poisonous gas, and it is also extremely corrosive to carbon steel. Currently, there are a few methods for this vaporization process, such as the absorption, and conversion, which includes the cloth and locate process. However, Currently, the current conventional methods have major drawbacks such as the intensive energy process and suffer with degradation and activation of catalysts. As a result, it leads to lower sulfur production and high cost operation. Therefore, a new green approach has to be proposed, such as by using the ionic liquids which are salts with low melting points below the 100 degrees Celsius, and is also known as the designer solvent because we can design its properties by just changing the cation and anions, as well as it is an environmentally friendly solvent. So for this project, we are using a specific type of ionic liquids which is called as task-specific ionic liquids, TSILs, which is a unique subclass of ILs that is structurally functionalized to serve for a particular purpose of reaction. Commonly, TSILs with metal compounds are used for gas separation. That is the reason why we are using for metal chloride anion-based ionic liquids. This is because metal chlorides alone are able to oxidize the hydrogen sulfide to elemental sulfur. Hence, it can be incorporated into the ILs matrix to form TSILs. And the extent of H2S conversion depends on the oxidation state of the metal used in the chlorides, and expected that such TSILs can potentially promote faster conversion of hydrogen sulfide to sulfur. Hence, metal chloride anion-based ionic liquids are proposed to overcome the formation challenges and drawbacks of the commercial processes. Then we will proceed to the research objectives. There are three objectives. The first is to screen the available metal chloride anion-based ionic liquids for their potential for direct conversion of H2S. Second is to synthesize and characterize the selected metal chloride anion-based ionic liquids. And last but not least is to perform the direct conversion studies for hydrogen sulfide in metal chloride anion-based ionic liquids. These are the scopes of the research. The ionic liquids used in the metal chloride anion-based ionic liquids, and the screening will be conducted by the conductor-like screening model for real solvents, Cosmos S at room temperature and pressure, and the selection of ILs will be based on the performance index, the safety reasons, and the economic value. And the total number of ILs selected for the synthesis is only 3 out of 300 IL screened, and the characterization will be characterized by using the methods as you can see here. And the conversion studies will be performed at room temperature and pressure at a concentration of hydrogen sulfide lower than 100 ppm. Basically, we will proceed to the Cosmos S screening, which involves two major steps. The first one is the generation of Cosmos part and Timor X. The generation part is where we are going to construct the structure that is going to be used for the screening process later on. After we have prepared the structure and constructed inside the Timor X, we are going to use the same structure for the screening properties by using the Cosmos term X. From here, we can just list all the properties that is needed and use the Cosmos term X to get the information needed. Okay, then we will proceed to the results and discussion part. Basically, there are 5 major parts for the results and discussion. The first one is the Henry's law constant, which is to determine the solubility of ILs in the hydrogen sulfide. The activity coefficient is to evaluate the selectivity and capacity of ILs, and also to obtain the selectivity, which refers to the ability of ILs to promote the reaction which favors the hydrogen sulfide over oxygen to yield the desired product, which is the elemental sulfur. And the capacity refers to the ability of ILs to contain the maximum amount of hydrogen sulfide. And last but not least is the performance index, where we predict the IL's performance in the conversion of H2S. Before we start our discussion part, we need to understand the electronegativity of metals in metal chloride anion-based ILs. This is because electronegativity of metals in metal chloride anion-based ILs play a major role in affecting the selectivity and capacity of ILs. It refers to actually the atomic ability to attract the electrons from the atoms bonded to it. As a result, electronegativity of metals will also affect the performance of the metal chloride anion-based ILs for direct conversion of hydrogen sulfide into the elemental sulfur. Based on table 1, after this, gallium is the most electronegative metals, followed by iron, gold, aluminium, and indium. Meanwhile, the least electronegative metal is titanium. As you can see here, this is the tables of metals electronegativity in the metal chloride anion-based ILs. Then we will proceed with the selectivity. Selectivity is affected by the cations and anions of the metal chloride anion-based ILs. For the cations, the phosphonium-based ILs display a very high selectivity compared to the rest of cations. This is because cations with the aromatic rings such as pyrrolinium and phosphonium have higher selectivity than those with aromatic rings to the absence of steric hindrance. Steric hindrance reduces the hydrogen bonding between the cation and the heteroatoms of the polyaromatic molecules, hence resulting in lower selectivity. The order of selectivity increases from pyridinium to imazolium, pyrrolidinium, and phosphonium. The selectivity is also affected by anions and is found to be related with the electronegativity of anions. Higher oxidation state elements are more electronegativity as they are more capable to attract and stabilize the electrons. As a result, the selectivity for H2S increases as the oxidation states of the metal used in metal chloride anions increases. This is the graph of selectivity at infinite dilution for hydrogen sulfide over oxygen in 300 ILs at 288.15 Kelvin. There are four base ionic liquids: the imazolium, pyridinium, phosphonium, and pyrrolidinium. Next, we will proceed to the capacity. Capacity also affected by cations and anions, and capacity has been found to be increasing when the pi electron cloud of cations is decreasing. This is because the presence of nilor class electrons in the cations with aromatic rings causes a strong steric hindrance toward the heteroatomic polyaromatic compounds. As a result, they possess a lower capacity for hydrogen sulfide molecules. The capacity increases in the order of imazolium, pyridinium, pyrrolidinium, and phosphonium. Capacity is also affected by anions. The hydrogen sulfide capacity is found to be inversely proportional with the electronegativity of anions. This is because, for example, hexachlorotitaniate anion 3ICl6 base ILs which possess the lowest electronegativity compared to the rest of the metal anions in the screening process, displayed a very high capacity for hydrogen sulfide absorption. This is because its low electronegativity has contributed to its high capacity for H2S molecules instead. This is the graph for capacity for all 300 ILs. Then we will proceed to the performance index. Performance index is actually the to evaluate the performance of the ionic liquids in conversion of H2S. Generally, the solvent which possesses a high selectivity tends to have a low capacity instead. Hence, it is not economically viable to choose a solvent which has better interaction but require larger volume instead. Thus, it is important to identify a solvent which possesses both properties in reasonable magnitude. Based on comparison of PI values of 300 IL, it is obvious that phosphonium-based ILs have higher PI values due to higher selectivity and capacity values respectively. This also indicates that the phosphonium-based ILs might give better result in the real conversion of H2S experiment compared to the rest of the ionic liquids, the rest type of ionic liquids. Okay, as you can see, this is the performance index for hydrogen sulfide in 300 ILs at 288.15 K. We can see the performance index increases from pyridinium to imazolium to pyrrolidinium and phosphonium. Then we will proceed to the selection of ILs for synthesis. Based on the PI values predicted by COSMAR-S on 300 ILs performance in H2S conversion, trihexyl tetrahedral phosphonium ion P614 and tetrabutyl trihexyl phosphonium ion P414 were the two best cations of ILs after being compared with every anion in the screening process. Recent findings reveal that ILs containing P4414 cation are extremely toxic and carcinogenic to human beings. As a result, this production has been stopped. Therefore, P614 cations is selected for synthesis for safety reasons. In the economic side, iron trichloride and tin trichloride are much cheaper in cost compared to the rest of metal chlorides. Therefore, by comparing in terms of performance index, the safety reasons and economic values, 3 ILs were chosen for synthesis, which is trihexyl tetrahedral phosphonium tetrachlorogallate, trihexyl tetrahedral phosphonium tetrachloroferrate, and trihexyl tetrahedral phosphonium trichlorostenate. These are the tables that represent top 20 ILs out of 300 ILs in terms of performance index, and these are the selected ILs. Okay, last but not least, I would like to conclude my presentation with this. In order to identify the best possible reaction media for forming the H2S conversion, a total number of 300 ILs from a combination of 20 cations and 15 metal chloride anions was screened by a COSMAR-S model simulation. The thermodynamic and physicochemical properties are also obtained and analyzed. By considering several important factors, a series of these ILs containing cation of trihexyl phosphonium P614 with anions of tetrachlorogallate, GHL4 tetrachloroferrate, FeSl4, and trichlorostenate SNCl3 was selected for photosynthesis. Consequently, the physical chemical properties such as density, viscosity, thermal properties, as well as conversion performances induced the SILs will be systematically investigated. That's all from me for now. Thank you for listening and for your attention. We will proceed with the Q&A session. Thank you.
Much the presentation from Mr. Muhammad Shahil. Okay, now let us see if there's any question for Mr. Muhammad Shahil. Okay, we have one question from I think here. Okay, so what does the ionic liquid do to S2S? Is it oxidizing S2S?
Okay, thank you very much for the question, Dr. Cecilia. Actually, my else is functioning as a catalyst. This is as a reaction media for conversion of H2S. Basically, yes, the else will be as an oxidizing agent for H2S. It will oxidize the hydrogen sulfide into elemental sulfur. Basically, the theory behind my selection for metal chloride anion-based anionic liquids is by referring to another very efficient industrial desulfurization process, which is locate process. So basically, locate is also using a metal chloride anion, metal chloride based type of reagent to oxidize H2S into elemental sulfur. So basically, I try to assimilate the same concept into IELTS, but it is more efficient because it is regenerable and also environmentally friendly. I hope it will answer your question.
Okay, thank you so much sharing from Mr. Muhammad Shahil. I hope it answered the question by Dr. Cecilia. Okay, any more questions from if so? Okay, perhaps there is one question from me here to Mr. Muhammad Shahil. So I can see this is a very good work. Okay, to try to select the uh, ionic liquid for optimizing the performance of conversion for H2S. I would say that is right. Okay, so when you do the testing, so you find out something like is there any other way further optimize the H2S performance? Is some other way to modify ionic liquid or some other something like that? You can share with us your opinion.
I think the only way to get a better understanding is by getting more type of onion liquid for screening. I think maybe we can screen more so that we can have a large variety of onion liquids. So that maybe there are still a few type of onion liquids that are not screened that might have some potential for a very high conversion. But so far I am doing what my work base is. I have tried to refer to the literature and try to
Hmm.
obtain all the listed literature so far and try to do the screening based on the listed literatures. And so far, I can only manage 300 IELTS for the screening process. So maybe if there is some need for another higher potential, maybe we can do more screening, like 500 or 1000 maybe, but it will take some time to complete.
Yeah, 300 is quite a big amount, big value, I would say.
Yeah.
So I would say great job for you because at least you can screen by comparing the 300 onion liquid.
Yes, thank you.
Okay, yeah. So I would say now we do not have any more questions from Mr. Muhammad Shakil. Okay, once again, thank you so much for your presentation. Okay,
Thank
good
you.
day to you. Bye bye.
Bye.
Okay, next, let us welcome Ms. Aida Shafika Abdumana from University Technology Petronas for her presentation on a project entitled Optimization of Slow Pyrolysis of Bamboo for Biochar Production using Takuchi L9 Ogogona Array. Okay, let's welcome the presentation from Miss Aida Shafika.
Good day to everyone. My name is Aida. I will be presenting on behalf of my colleague for a paper title of Optimization of Slow Pyrolysis of Bamboo for Biochar Production using Takuchi L9 Orthogonal Array. So these are the presentation outline for today. We have introduction, methodology, result and discussion, and last but not least, conclusion. So as we know, Asia are the most bamboo resources compared to Africa and also America. In Malaysia, we produce a total of 7 million tons of bamboo, where 6,000 tons from it coming from the commonly used bamboo. So there are also bamboo industry that we commonly use, which is fabric, furniture, and also flooring. So there's a lot of bamboo waste coming from the bamboo industry, which actually cause major problem during the landfill. So the solution is we need to produce a value-added products such as biochar, paving blocks, pellets. These are some of commonly bamboo value-added products. And the significance of bamboo for biochar production, which is coming from the bamboo characteristic itself, and also where it is rapidly growing, have a low sulfur, nitrogen, and ash content, mainly composed of hemicellulose and cellulose and lignin, will make it interesting to produce into valuable product. So the bamboo as a biochar, it is because the surface area can be increased. It's used to improve soils and iron exchange capacity. It also being used as a fuel. So these properties of biochar will be depends on the feedstock that we use, atmosphere, particle size, holding time, temperature, and also heating rate. So moving on to the methodology, we have materials where we use bamboo and also nitrogen gas. The equipment will be precision scale, autoclave pyrolysis reactor, convection drying oven, multi-mile grinder, analytical sieve, shaker, and statistical software, which is MiniLab 17. So these are the general idea of our experiment where we use bamboo as a feedstock, and we observe 3 different parameters, which is reaction temperature, particle size, and nitrogen flow rate, where we determine the ranks by using Taguchi L9 orthogonal array. And the equipment that we use is autoclave pyrolysis, where we want to get the gas, liquid, and also solid char. However, the most important thing here is we want to see the solid yield and also the optimum parameter that can be used through the optimization done by Taguchi L9 orthogonal array. So these are the experimental procedure. First, we use 1 kg raw bamboo and we crush it into 1 to 20 mm size and dry at 105 degrees Celsius for 24 hours in the oven. Then we grind and sieve into 100, 500, and 1000 micrometer. Run the experiment based on the Taguchi L9 orthogonal array. Collect the product and weight the liquid and solid product, and collect the data on the product yield, which is all the product, which is gas, liquid, and solid, and find the maximum yield of biochar based on signal to noise ratio to find the optimal parameters. So these are the reaction parameter and the levels that we use. As we can see, for the reaction temperature, we use 300 to 500 degrees Celsius. For the feedstock, we use 100 until 1000 micrometer. And for the nitrogen flow rate, we use 100 to 500 ml per minute. So we use this array method because we want to have a minimum run instead of 27 runs. So the right hand table shows that the number of runs that we will using with the factor A until C. So these are the result and discussion for our experiment. As you can see, these are the total percentage of product yield. We rate every yield that we found, which is gas, liquid, and also solid. But we can see that at the third run, the solid yield are the highest compared to others. Meanwhile, at the 7th run, we can see that the liquid and also gas yield are the maximum compared to the others. But in terms of our experiment, we want to see the biochar yield instead of at yield. So with the graph at the right hand side, you can see that the particle size, by increasing particle size, we can see that we can increase the solid yield with every reaction temperature. However, at this moment, we can see that 300 degrees Celsius will be the optimum, where it has the highest yield compared to other temperature. So these are the graph for 3 parameters, which is reaction temperature, feedstock particle size, and also nitrogen flow rate. As you can see at the nitrogen flow rate graph, there is slightly inclined, but we can see that the yield is not that affected by the nitrogen flow rate, where compared to reaction temperature and also feedstock particle size. Okay. And then from the optimization of solid yield, we obtain that we find 3 to 10.7% difference from the predicted value. As you can see, we highlighted the run that we have done based on the temperature on the array, and the others are predicted by the software. So as a conclusion, we found out that nitrogen flow rate have no significant effect as particle size and also reaction temperature. So the optimal condition will be 100 ml per minute for nitrogen flow rate, 1000 micrometer for particle size, and optimum temperature will be 300 degrees Celsius for maximum biochar yield, which is 52.11%. So last but not least, we want to acknowledge the Ministry of Education Malaysia for awarding the highest institution of Center of Excellence SOE status to CBBR with grant number 015MAO-052, also National Resources for the Bamboo resource. And these are the list of reference used for this experiment, and we open for Q&A session. Thank you.
Okay, thank you very much, Miss Aida Shafika, for the interesting presentation. So let's move on to the question from the audience. So let's see. Okay, I can see there's one question from Associate Professor Dr. Abdul Halim. It is actually our department chair. According to the questions, why higher particle size give better yield value? So perhaps Ms. Aida Shafika, you can further share with Dr. Halim.
Hello, can you hear my voice?
Yes.
Yeah. Okay, thank you, Dr. Halim, for giving me the question. Actually, this is what I think lah. Okay, so maybe because of it have a larger surface area compared to other particle size, maybe that's why it is have rapid reaction and resulting in higher yield compared to the others.
Okay, thank you sharing from Ms. Aida Shafika. So I hope this answer the question by Dr. Halim. Okay, so meanwhile, let us see if there's any more questions from the audience. Audience, as a reminder, if you have, please drop your question in the icon for live Q&A, or okay, kindly drop any question over there. Okay, the presenter will answer your question accordingly. Okay, while waiting for the question from the audience, maybe I have two questions for you, Ms. Aida Shafika, if you can share with us. Okay, so I can see one of your factor is temperature. Okay, so you in from the range of 300 to 500 degrees Celsius, right?
Yeah.
Okay. If I try to study, perhaps at 700, is it possible for the pyrolysis to be occur?
Oh, can you repeat again?
Okay,
possible to?
Okay, let's maybe I ask in such a way. Okay, is it possible if I try to investigate the temperature at temperature values which is out of the range of 300 to 500 degrees Celsius.
Okay. I think I have read some of the articles that they use 700 degrees Celsius
Yes.
for the pyrolysis,
Mhm.
but maybe will give different effect on the solid yield or maybe different effect on the product itself for
Mm,
the application. Yeah.
mm. So let's say if the experiment is going to be investigated at higher temperature, what in your opinion what will happen to the yield, for example?
Okay. For as what I see for my experiment,
Yeah.
the relation is that when we increase the temperature, we get a lower yield. Right. So I
Oh,
am expecting lower yield compared to the at high temperature. Yeah.
yeah. That's why you investigated your process up to temperature of 500 degrees Celsius only. So
Yeah.
this point, okay, okay.
Yeah.
Maybe since there's still no more question from all, maybe we can move to the second question from me. Okay,
Okay.
I can see you have three parameters, right? Like the
Yeah.
temperature, particle size, as well as nitrogen flow,
Okay.
right? Okay, in your opinion, is is it necessary to study other factors as well for the pyrolysis process? For example, for your project?
What you mean is the other parameters of this experiment, is it?
Yes. Besides particle size, temperature, nitrogen gas flow, what are
Yeah.
the potential other factors or other criteria that you need to take into consideration?
Okay. So basically, there are some other parameters such the different type of feedstock also will give different
Mm,
kind of yield. Yeah. Maybe different type of bamboo have different yield. We don't know because we have maybe different composition in the feedstock. Yeah, and then the holding time of the pyrolysis may give different effect. I think that's all that I remember. Yeah.
mm, okay. Thank you so much
Okay.
for your sharing again. So I try to check the live Q&A and discussion forum. Okay, seems like there is no more question for Miss Aida Shafiq audience. So again, thank you so much, Miss Aida Shafiq, for your sharing. Okay, have a nice day. Bye bye.
Okay. Thank you. Bye bye.
Okay, with this, let us welcome the last presentation from the presenter, Miss Mahana Ismail from University Technology Petronas. So Miss Mahana Ismail project, it is about screening of gallic-based metal organic framework for single component CO2 and CH4 gas. Without any further delay, let's welcome the presentation from Miss Mahana Ismail.
Assalamualaikum and hello to all. I am Marhaina Ismail from Chemical Engineering, University of Petronas. We will present about screening of caloric-based metal organic frameworks for single component CO2 and CH4 gas. Natural gas fields with high CO2 content up to 87% in Malaysia made it unconventional since the gas has low heating value. The removal of CO2 is necessary to provide high purity of natural gas and to meet the partner standards to prevent corrosion. Physical adsorption is widely used in CO2 capture since it offers potential energy saving with low cost compared to absorption, membrane, and cryogenic. Adsorption is a surface phenomenon occurred when the absorbate is attached to the surface of adsorbent. Absorption is highly depending on the solid absorbent such as zeolite and activated carbon. Nowadays, metal organic frameworks have gained attention in various fields. MOF is a porous hybrid organic-inorganic material that has a strong coordination bond between a metal and and an organic linker. MOF have unique properties such as large surface area, well-organized porous structures, and easily tailored functionalization. MOF have three main parts, which are metal ion, organic linker, and empty spaces. Since MOF can be designed, their structures and property can be tuned by the choice of their building blocks. And this enables the selective gas absorption that is not attainable by the conventional adsorbent. However, one of the most significant drawbacks of MOF is the high cost of organic linker. Gallic acid has advantages over expensive organic linkers due to low cost, low toxicity, easy availability, and naturally abundant. Gallic acid is proven can act as a successful organic linker for gallic bismuth, or known as M-gallate. Gallic bismuth have advantages such as readily available linker, high stability, high recyclability. Initially, gallic bismuth have been used in biomedical applications. Recently, they are gradually reported for the adsorptive separation of light hydrocarbon, such as separation of ethylene-ethane mixture, acetylene-ethylene mixture, and geometric isomers of 2-butane. Among the underreported works that might have a great opportunity is separation of carbon dioxide and methane. Screening using a systematic tool is very important in order to understand the interaction between MOF and the gas molecule. Molecular modeling provides estimation on selectivity, capacity, adsorbent selection. Grand Canonical Monte Carlo GCMC method is widely used for molecular modeling on MOF for CO2 capture. It can provide the prediction on the adsorption isotope. Various types of MOF structure can be tested without synthesizing, and therefore can save cost and time, since it can even replace the experiments. Therefore, it allows the discovery of a large number of possible materials for a specific application. Based on the previous studies, the reliability of GCMC is proven, whereby the simulated and experimental results are well accurate and almost perfectly overlap to each other. GCMC simulation can be performed using sorption module in Material Studio in order to compute a loading curve for molecules on MOF. This work is to study the applicability of gallic acid as alternative linker in MOF using computational approach, and their predicted performance are evaluated and benchmarked with available literature data. Next is the methodology. Figure 2 shows the flow chart of simulation for sorption module in Material Studio. The structure of CO2 and CH4 are drawn in the Material Studio, while the most structures are imported from Cambridge Crystallographic Data Centers, CCDC. Next, clean the structure of components and make sure they are linked to each other. These are the structures involved: CO2, CH4, and M-gallate. Then, set the parameters for calculations. These are the parameters are described accordingly as shown in table 1. Next is run the sorption module, and lastly, end of the process. For result and discussion, I will present about the predicted single component adsorption isotope first. As we can see, the amount of CO2 absorbed is increasing as the pressure increases for all the gallic bismuth, and the amount of CO2 absorbed is significantly higher than CH4 with a type 1 isotope shape. At initial phase of adsorption, CO2 molecules are in contact with gallic bismuth surface and form monolayer gradually. A steep CO2 loading can be detected at the low pressure range. For CH4 adsorption isotope, most of the gallic MOF display roughly linear plots indicating that the frameworks are not saturated with CH4 at this operational condition. Therefore, these are potential adsorbents for CO2 CH4 separation. Based on the predicted adsorption isotopes, adsorption capacity and stability of gallic bismuth at ambient conditions can be determined as shown in table 2. The adsorption capacity is an important parameter in evaluating more for CO2 absorption. However, this approach cannot estimate the binary gas absorption because it is not considering the competitive absorption among the different components in a gas mixture. As we can see, all the capacity values for CO2 are higher than CH4. CO2 has kinetic emitter of 3.3 angstrom and CH4 is 3.8 angstrom. The pore aperture size of gallic bismuth are in the range of 3.47 angstrom to 3.69 angstrom. Therefore, gallic bismuth are theoretically capable to selectively capture CO2 from CO2-CH4 mixture based on the size differentiation. Furthermore, CO2 has a larger polarizability and quadruple moment which lead to a stronger interaction between CO2 and MOF. The highest predicted capacity is achieved by mg gallic with 7.79 millimole per gram, and the lowest is achieved by Ag gallic with 6.35 millimole per gram. Since the capacity of CO2 is higher than CH4, therefore all the selectivity values are more than unity. The adsorptive selectivity occurs due to the difference in affinity of components in the gas mixture to be attached on the porous surface of MOF. Selectivity can be simply understood as the affinity of gallic bismuth to adsorb CO2 compared to CH4. Therefore, it can be concluded that gallic bismuth are prone to selectively capture CO2 compared to CH4. Since the experimental results on the adsorptive separation of CO2-CH4 using gallic bismuth are not available in the literature, therefore the predicted capacity is compared with the other absorbents in the previous experimental work as shown in table 3. In terms of CO2 absorption capacity, mg MOF 74 still tops the list of all the absorbents. However, when it is compared to gallic bismuth, mg MOF 74 is so costly. Nevertheless, mg gallic shows higher predicted capacity compared to the rest of other absorbents. Lastly, the conclusions are computational screening of MOF is a great opportunity to identify the potential materials for CO2 capture. Gallic bismuth can be a new promising absorbent in CO2 capture as the predicted CO2 loading is significantly higher than CH4. The highest predicted CO2 absorption capacity is achieved by mg gallic and the lowest is by Ag gallic with 7.79 millimole per gram and 6.35 millimole per gram respectively. The applicability of gallic acid to act as an alternative linker in a new familiar hybrid metal organic framework is relevant for practical applications. So this is the references, and I think that's all. Thank you.
Okay, thank you very much, Ms. Mahana Ismail, for sharing. Now let us open to the floor for any questions. Audience, if you have any questions, please drop your question in the icon for live Q&A or discussion forum. Let's see if there is any more question for Ms. Mahana. Okay, while waiting for the question from the audience, maybe I could. Okay, there is one question from Dr. Otori. Okay, there is one question from Dr. OHG. Okay, the question is still there is not activity of galette-based MOF at 1 to 2 only. Any way to improve this?
Okay, thank you. Can you hear my voice?
Yes.
Okay. So thank you, Dr. O, for the questions. Okay. Firstly, this is a simulation result, the predicted. But for the prediction, I think I can do more because simulation is just the study. To prove the applicability of gallic acid as organic linker for gallic bismuth to be used as absorbent in adsorptive separation of CO2-CH4. But for experimental absorption selectivity, I think I can improve by washing technique. Means that I need to activate the open metal site by washing to provide better affinity site for CO2 to be attached on the surface of moth.
Okay, thank you, Ms. Mahaina, for the answer. So just to further share with you, perhaps beside washing procedure, perhaps you can think of any other post-treatment method in order to further modify the MOF. Yeah, that I think that will help to possibly improve the performance as well.
Okay. Okay.
Yeah. So I hope the answer from Ms. Mahaina is to answer the question from Dr. Obi Ching. Okay, let us see if there's any more questions for Ms. Mahaina. Okay, Ms. Mahaina, perhaps I have some questions for you here. Okay, if I'm not mistaken, from your presentation, you did investigation on the screening for the MOF by targeting single CO2 and CH4 gas formation. Am I right?
Sorry, Doctor, not clear.
Because from your title and presentation, it seems like you do the screening for the MOF based on single CO2 and CH4 gas, right?
Yeah.
Okay. So will there be any difference by based on CO2 and CH4 gas mixture?
Oh, actually, I have done it for several meter. The capacity is quite low if I did for binary, because there is some competition between the components in gas mixture. It's quite different.
Okay. When you mention lower capacity, are you referring to lower selectivity?
Lower capacity normally will cause lower selectivity normally.
That means when you did experiment or you did investigation for single gases and binary gas mixture, actually by having single gas, it will enable higher selectivity. Can I say so?
Yes. Yeah.
Oh, I see. Okay. There is still no more question from the audience. Perhaps last question from me. Okay, so this work you have done actually by targeting CO2, CH4 gas formation and separation. So do you see if this galette-based MOF, it is very potential for other type of separation as well, for example, CO2 N2?
I think can, because Doctor, actually galette-based MOF is quite new in azotic separation of hydrocarbon. In oil and gas industry. Okay, because this framework before this have been used in biomedical application. So since starting from 2018, there is a group to study for oil and gas industry. So it's very very scarce of study about this in this current time.
I see.
So I think it's possible because based on the pore aperture, theoretically we can separate CO2 from N2 as well.
Yeah. Okay. Thank you very much for the sharing from Ms. Mahana this time. Thank you so much. Good day to you.
Thank you, Doctor.
Bye bye.
Okay, thank you, Doctor. Bye.
Okay, so there was the final presenters for our parallel technical sessions. Thank you very much to all the presenters for the shared knowledge and information. And to the audience, I would like to thank you for joining us today, for the time and interest throughout the whole session. Thank you. And I would like to invite all the presenters and all the audience to our opening ceremony for Icpeam 2020 at 2 p.m. later. Okay, with this, thank you so much again. Bye bye. Take care.